So let's go back to the acid version. We're mostly going to focus on that. And hydronium equals the acid over the base times Ka. Well, one thing you can do is take the negative log of both sides of this reaction. Now, negative log hydronium is pH, and that's not a big deal. Minus log of the right-hand side, in the logarithm world, you can break that up. You can break that up into minus log Ka plus minus log acid over base. Now, minus log Ka is pKa. That's something we've seen a little bit or talked about. And minus log acid over base is the other part that's listed. So what happens a lot of times, people will flip the acid and base. And in the logarithm world, that turns the negative into a positive. You change the sign. So you end up with what's called the Henderson-Hasselbalch equation, pH equals pKa plus log base over acid. And this is one of my favorite equations, believe it or not, of the whole Chem 221 through Chem 223 series. It's for buffers. It can be used for other things too, but buffers is the primary thing. And it shows how the pH of a buffer depends on the pKa, the strength of the acid you put in, as well as the ratio of the base to the acid. And we'll talk about this here coming up. Henderson-Hasselbalch, the HH equation, is pretty cool because it really shows that the pH of a buffer depends on the ratio of the acid to base as well as the strength of the acid, the pKa. And they're kind of independent things. And we'll talk about how to make use of that here in just a second. But wow, the HH equation is the bomb when it comes to dealing with buffers. I'm letting you know that right now. Because it's a ratio, we usually use moles per liter over moles per liter. That's the standard ice table kind of thing. But you don't really have to have concentrations of acid over base or base over acid. It really could be the ratio of moles. So you could have just the moles of base over moles of acid. So this gives you a lot of flexibility. You can use log concentration over concentration, but you can also use log of moles over moles. You can use the one which is easier. And because volume doesn't play a factor, you can take a buffer and just add a bunch of water to it, dilute the heck out of it, doesn't change its pH, which isn't crazy. Now, if you made it like, the volume of, I don't know, Lake Erie or something like that, maybe there'd be some changes. But in a normal chemistry lab, you can just add tons of water, same pH, which is pretty crazy. Henderson-Hasselbalch is cool because, first of all, there's no effect on volume. You can add as much as you want, doesn't affect the pH. But also what's really important, you can use moles or molarity for acids and bases, whatever is easier for you. And that can have some serious implications, as we'll see in a little bit. Here's an example. We have acetic acid with a Ka value. Now, pKa equals minus log of Ka. So minus log 1.8 times 10 to the minus 5, 4.74. So that's where the pK value comes from. So we're going to prepare a buffer. It's got acetic acid and sodium acetate. Again, acetic acid is the acid, sodium acetate is the base. It's going to have a pH of 5. So what ratio of base to acid do we want? All right. So this question at first looks a little strange until you figure out how the Henderson-Hasselbalch works. We want a pH of 5. And that's going to equal pKa 4.74 plus log. And the ratio, I'm just going to call x. That's going to be the ratio of the base to the acid. So you want to solve for x. So 5 minus 4.74 will give you some number. You then get rid of the logarithm number by going 10 to the x. That's the anti-base 10 log. If you do all of that, you're going to get a ratio then of 1.8. So you can see once again what happened there. We wanted a pH of 5. pKa 4.74. 5 minus 4.74 is 0.26. And then to get rid of this base 10 log, you go 10 to the power of. So 10 to the power of log just cancels out. 10 to the 0.26, 1.8. So 1.8 is the ratio. And what that tells you is you want 1.8 times more base than acid. So if you put 1 mole of acid in, you want 1.8 moles of base in, stuff like that. It's pretty handy. It's a great way to figure out how much base and acid you can use, stuff like that. So here's a question. We want to figure out the pH when we add a milliliter of 1 molar HCl to a liter of pure water. And before it was HCl, we'll assume it was perfect at 7.00. But we also want to add the same 1 milliliter of 1 molar HCl to a liter of buffer that has acetic acid and acetate at those concentrations we used earlier. And we saw that they were pH of 4.68. All right, no problem. So to solve for the first one, pH to pure water, it's going to be minus log of hydroxide. So you need the moles of HCl, and you want to divide by the total volume. So if you do that then, first we're going to have to use M1V1 equals M2V2 to solve for the new concentration of the HCl. So 1 milliliter of 1 mole per liter HCl would be the M1 and V1. We're going to solve for M2 and the total volume, 1,000 plus 1, 1,001 milliliters. So the concentration comes out to be 9.99 times 10 to the minus 4 moles per liter, minus log of that number, pH of 7. So our 1 milliliter made the pH 7 drop to pH 3. Pretty heavy drop of pH. But again, this is the effect of strong acids. And again, non-buffered things will drop pretty fast if you have an acid added to them, or rise pretty fast if you add a base. But now let's do the same problem with our buffer. If you're going to do it this way, and I'll tell you a better way here in a little bit, first what you have to do is figure out the effect of the strong acid or strong base. So in this kind of problem, if you use moles per liter, the acetate, the base, is going to go down upon adding the hydronium, and it's going to use up all the hydronium because it's 100 killer from HCl. So at the end, you're left with 0.599 moles per liter acetate. But as much as the base goes down, the weak acid is going to go up, because this is how buffers work. The strong acids wipe out some of the base, but in the process, the conjugate acid comes up. So you can see there what's happening. The acetic acid is going to jump then to 0.701. So these are our new concentrations after the HCl has been neutralized, and from this point now, we have to figure out what the new pH is. So at this point, we're going to go back to that acetic acid and water, making hydronium and acetate. We'll use the same things, but with our new values. So we're going to end up with 0.701 minus x, 0.599 plus x, and x. We can ignore that little x relative to 0.701 and 0.599 like we did in the last one, and we'll basically just solve for x, the hydronium. So if you do that, hydronium equals acid over base times Ka, 0.701 divided by 0.59 times the Ka. Hydronium comes out to be 2.1 times 10 to the minus 5, minus log of that number, and lo and behold, 4.68. And that was the pH before the HCl was added. So the buffer absolutely resisted the change of pH from the HCl. It dropped the water from pH 7 down to pH 3, but that same amount of acid didn't affect the buffer at all, and this just shows how powerful the buffers can be. Now the HCl did affect the buffer, all right? That's why the acetate went from 0.6 to 0.599, and the acetic acid went from 0.7 to 0.701. So it did make a difference. It's just is so insignificant compared to the rest of it. It had no effect on the overall pH, which is crazy. So strong acids and strong bases don't have the same effect on buffers as they do on, say, pure water, which makes them kind of useful. We can also use the Henderson-Hasselbalch for problems like this, and this is something I highly recommend you master. It's a really cool skill. If you rewrite the Henderson-Hasselbalch for moles, you end up with this expression where pH equals pKa plus log moles of base minus moles of strong acid divided by moles of weak acid plus moles of strong acid. So in the last problem, the HCl knocked the conjugate base, the acetate, down a little bit. That's why it went from 0.6 to 0.599. But it added to the weak acid. So the acid went from 0.7 to 0.701. And this is the same effect here. You can see how the acid lowers the base, but it ends up adding to the weak acid. So you need pKa minus log of Ka is 4.74. No problems there. You can plug all that stuff in, and when you do that, wow, 4 4.67. Now, the ice method we used earlier, which I call double ice, because the first ice was taking care of the strong acid, and the second ice table was dealing with the new buffer you had, the new weak acid with its conjugate base. So that's a double ice system. That system gave 4.68. My cool Henderson-Hasselbalch equation here gave 4.67. And unlike the last example where I had to put on more than one slide, I can put all of this on one slide, which is pretty cool. So I do think Henderson-Hasselbalch is a great time saver. It's great about dealing with strong acids in buffers, and as we'll see on the next page, also with strong bases in buffers. It really makes the calculations a lot easier. Double ice is tedious, but man, Henderson-Hasselbalch, rock on. So if you add a strong acid to a buffer, this is the version of the Henderson-Hasselbalch that's used. pH equals pKa plus log. The base goes down with the strong acid, but the weak acid actually goes up with the strong acid. That's how this works. If you add a strong base to the buffer, it's very similar. The strong base will add to the weak conjugate base, but the strong base will lower the weak acid. So you can see kind of the values there are different. Like it's add on the top and subtract on the bottom for the base. The acid was subtract on the top and add on the bottom. And these can be super useful, and I used them sometimes when I made buffers. I highly recommend good old Henderson-Hasselbalch. So here's a question to think about buffers. We're adding a small amount of strong base to a buffer, okay? Now, strong bases will make your pH go up. You'll have an increase in pH. So it's not going to decrease C, D, and E. Those would be acid problems, not base things, okay? So the base is going to make your pH go up, but does it go up from the strong base, or does it go up because of the weak base of the buffer? And I would absolutely argue that it goes up because of the weak base of the buffer. The strong base will be neutralized by the weak acid, and in the process the weak acid concentration will go down, the weak base will increase. So it goes up because of the weak base, and it's a much smaller increase, all right? So that's why these things happen, stuff. It's not the strong base or the strong acid, it's the resulting effect on the conjugate system which makes the changes to the pH, which is kind of a cool thought.